Hello, and thank you for joining me on this machine learning tips video. We're going to be talking about LightGBM, which is a very fast model. It's not a model I've used a lot, but I'm going to start making it part of my repertoire. It is a model from actually designed by Microsoft, and what it really specializes in is being very fast. And so this is a good production model, one that you'd want to use when you're actually making when things speed really counts and stuff like that. And we'll go through today and see if we can how it performs in comparison to gradient boosting, and we'll compare it to XGBoost as well because why not? We're here. um, and so importing the basic data science libraries from import LightGBM as LGB. From scikit-learn ensemble, import gradient boosting, and then from XGBoost, import XGB regressor. Okay. Got our some other scikit-learn stuff for scikit-learn. Even if you're not using it forever for your model, it still has so many good tools for processing that we use here and turning off some warnings. So just a note, you can't turn off all of GB's warnings. They display stuff that is always kind of on output. So this will turn off some other warnings more for scikit-learn and stuff. Okay. Going through the concrete compression data set, I'm going to make this a little bit harder prediction though and try to predict water instead of the CSMPA. I've used this a few times for these lessons. This is a really good harder data set. We're predicting kind of this water. Hard, but not too hard. So we can kind of really get to see the effect of how the models are performing on more or less real data. Well, I believe this is actually a real data set. So it's really good to, it really just has that extra texture that is really helpful in really evaluating these models. Okay. So doing some EDA. One of the things, if you haven't watched any of these tip videos yet, I am doing one hot encoding for the event of superplasticizer, phi ash, and slag. Being there's a lot of values is 0, and kind of the rest is more or less uniform. So I'm going to take this as an event if something's happening, and it did really make a big difference in the predictions. I did that to highlight that event of when it's 0 to help our model, again, just kind of highlight this is not part of the continuous variable, this is an event, and help in the predictions. Okay, so it's one hot encode that, and it did work well. And that's something you can do when you see a kind of abnormal distribution. Okay, so just binning the year column, so just kind of bucketizing this into 4 separate bins, and going to also do the one hot encoding of the slag, fly ash, and superplasticizer. What is equal to 0, multiply, this will create a true and false Boolean column, and then multiplying by 1 will create the ones and zeros, better for the machine learning model. Okay, then we're going to do features, water as the target, pulling the assigning to X, pulling the features out of my data frame, assigning to Y, pulling the target out of my data frame. Train test split, and going X and Y. Okay, so scalar equals then scalar, doing the fitting on the train, transforming the train and the test, doing the same thing for PCAs, fitting on the train, and transforming the train and test afterwards. So see, let's look at what we're here for. Quickly ran through the pre-processing. What we're going through here is the LightGB, XGBoost, and GradientBoosting. We'll compare all of them, but this is the workflow. It's a very different workflow for gradient boosting. XGBoost has a similar, if not exactly the same, but a very similar to the gradient boosting. LGM light gradient boosting model has a little bit, something a little bit more comparable to TensorFlow and how it works. Just that it actually prefers a data set versus a data frame, which is the square pandas format. It'll work the same for what we're looking for, but this allows it to distribute its training versus having it just in one spreadsheet. You can have a chain on many different GPUs because of the structure of this data set versus a data frame. Okay, and not super important for our talk today, so I won't spend a lot more time on that. But just notice that here we're doing lgb.dataset and we're putting an X train, and the label here is Y. Okay, so making the data set that we'll use to train our model. Here we're also going to give this parameters that we're going to try. So it's not, we're not giving this as arguments, we're making a param dictionary, and object is regression, metric is MAE, and this is almost where you can just uh, define the losses here, make it a little bit similar to the make it a little bit more similar to training a TensorFlow model, where really the loss becomes a bigger thing here. Okay, boosting type, gradient boosting. We'll see what this is, but this is gradient boosting decision tree. And this one right here. And we actually have selection, we have the ability to simulate something like a random forest as well. But this is just, we'll use this as we go through. This is a standard one for the gradient boosting type of comparison. Okay. So here we're going to do LGBM.predict, or so we're going to train it first, LGBM.train, param grid, dataset. Then we're going to do predict here. We don't have the dot score method like we do, or function like we do in the in scikit-learn. So what we can do then is we can predict here and give it to the R2 score that we imported from scikit-learn anyways, to give us an R score here. Okay, so this is the warning that I told you you really can't turn off. And this is basically just saying that it's going to keep trying to splitting until it can't find a better split. And so this is when the splits will stop when they stop adding value. Right here, it says negative infinity is the Gini loss, or the Gini gain, and negative infinity, basically negative 0. So there's no real gain anymore. Okay, so by default, I got a 99 on the train with the default settings, and a 92 on, well, basically 93 on the test. So pretty good. In comparison, our gradient boosting with the defaults on the test did 89, and the XG boost on the test did 90. So with the defaults, comparably a little bit better. Okay, so again, this is a really good model. It's a lot faster. And what I also did here is I did this. If you notice here, the magic word or magic commands. So it's the magic word, magic commands, percent sign, and then time. So it's going to time the time it takes to run just this cell here, the wall. And so if you see here, it took 7.755 milliseconds. Okay, so the wall time here is 7, so it's comparable to the gradient boosting and to the XG boost regressor 1.79. But we'll see after we play with some of the kind of hyperparameters and see if we can tune it a little bit better, and we'll see which one's the fastest one at the end. But it's very comparable in speed. It's the of the fastest ones here, very small microsecond, slower than the gradient boosting. But I think we'll find this is different after we've tuned the hyperparameters a little bit. Okay, so this talks about what is really different about the LGM. So I think one of the important things to mention about the LGM is that it's a histogram-based approach, and this allows it to narrow down the answer a lot faster, right? So it's able to do the splits in a much more kind of like almost binning, where it should do the splits, and so it just makes it a little bit more reduced than a continuous variable. Okay, so a little bit more easier. It has a few different sampling techniques that we'll play with as well. Gradient-based one-side sampling, which we'll play with as well. I don't know if it worked good, actually, truthfully, but it wasn't the best one. And so we'll play around with lots of the different settings and stuff. I'll let you read through all of the different things here, but one of the things is that it can actually do GPU acceleration as well, and that would be one of the reasons that I think we find it a little bit faster here as well. Okay, this is really meant to be more of a production model, and it does work well, but it is a really good high-speed production model. Okay. So to train the dataset, I'm going to make the train dataset here, lgb.dataset.train, and just set this up for my model down below as we go through the loops and try all of these. Okay, so first I'm just going to try and figure out which ones I want to use. So the gradient boosting decision trees, the dropout meets multiple additive regression trees, the DART, which is what scikit-learn random forest uses, okay, or the decision trees use in the random forest, and gradient based one-side sample. Okay, so we have a little bit different of the boosting types here that we can use. So I'm going to iterate through those, score for train, score for test. I'm going to iterate through those with my param grid right here and change the param grid each time. So it's a little bit more bulky, I guess you would say the code is, to do the scikit-learn. scikit-learn is super just easy to use, but that doesn't mean it's going to be the best model every time. Okay, and so train my model and output the fitted model. This is almost kind of like modern stats type of syntax that we see right here. Predict predicts on the train and test, and then score the train and test, and append that to my lists up above. Okay? Put those in a dictionary here, and so you can see that the GBDT, the gradient boosting decision tree, works the best. So a little bit of overfitting going on, but I was never able to correct this. I've never been able to correct it on this data set. So a little bit of overfitting happening, but still really our best score. 93 is getting to be a pretty good score. Okay, I'm sure we can do better if we really tried, but for the little pre-processing we did, not so bad. Okay, so doing a bigger loop here, doing kind of individually predicting the gradient boosting, XGBoost, and the LMGB a little bit, again, a little bit more coding here, but not so bad. Okay, doing a line plot for each one of those, doing the alpha down for the train version of this, and then we're going to see 3 different colors here, but for the gradient boosting, and then the XGBoost, and then the LightGBM. Okay, going to pull out the best scores of those with the argmax, which is the best scores, gives me the index position, and then from that I can pull out from the same list of estimators that we iterated through, which is the best estimator for each one of these. Okay, so let's check this out. And what's really interesting though is that we can see that the, seen by this color here, the test one right here, there's this kind of teal color, I guess you'd say, it is reaching a high maximum, its highest maximum, much sooner. So it needs a lot less estimators to perform well. So I think that's kind of an important thing here. I just went there really quickly. XGBoost just jumped right to its best score as well. So XGBoost would be, in terms of using less, it can get by with using less. I don't know if that was really the best model, but it did work well here. 140 turned out to be the best. So it was really performing slightly better over here. Well, you can see the XGBoost, or sorry, the scikit-learn gradient boosting. It took the longest and needed the most amount of models for performance best right here. So we got to 480. The best one for the gradient, the LGM, was technically again over here, but you can just very clearly see by this line that wouldn't even be statistically viable to say that it was actually better here. So this is a flat line. Okay, but so it's really interesting that it improved here quite quickly. Num leaves is something that we only have access to in GBD, or sorry, in the LGBM. Okay, so the light gradient boosting model. And so this I think is a really cool one because it's gonna do something similar as the min sample splits or the CCP alpha. Okay, where we're trying to tune that and allowing one side of our tree to grow while we stop the other side of the tree. So we're saying only use the let the trees grow where the leaves are adding the value, and reduce, chop off the ones that are adding the least value. Okay, so that's kind of cool. So we're going to cycle through that. Going to cycle from 2 to 40, and really, I mean, it's starting to make a difference having a certain amount, but you can see around 16 was the best, but you can see it with lots of 94s, 93s, 94s around the 16 and going all the way up to, that would be like 26. Okay, so likely our best numbers are going to be somewhere in this area, if not this one exactly. It'd be hard to say that on the test, but somewhere in this range, 16 to 26. Okay. Lambda 1, we can, another feature that's kind of unique to the light gradient boosting is we can tune this for the lambda regularization 1, regularization 2, so lasso and ridge types of regularization. So I'm just going to try them individually here, tuning the lasso regularization here, L1, iterating through a list of basically 0.1 going up by 0.1 and trying all of those up to basically 1. So from 0.1 up to 1.1, but not including 1.1. That's why I went above 1, because we just wanted to see kind of what it was from 0 to 1. You can go more than that, but generally it's not really viable, I think, in any sense. It's usually a portion, especially of L1. You usually, like we're finding here, you usually need a smaller portion of this. It tries to make the model too simple, and usually that can help and get rid of the worst ones, but it's generally good to kind of use most of the day when you make decisions. So this usually needs a little parameter, usually for lambda 1 or the lasso regularization. Okay, but it did make a huge difference in this data. So it's a really robust model is what I found. So tuning with these hyperparameters did not really always have an effect because of the robustness just inherent in the model. So we can see again that slightly better. So we're using 1.1 was the best for the regularization of the L1, L2, doing the same loop here, and seeing not getting a huge difference in either one of these, but 0.7 was the best one here. And so we'll use those kind of going forward in our model. So we can see here 0.7, 0.1. Another one that all of them have is the learning rate. So I'm going to try and tune all the learning rates together. The list of each scores, training the gradient, XGBoost, and light. So let's do all this here. Light gradient boosting model. Okay, doing the line plots for each one of these. And if we look at this, it's kind of interesting. They all behaved similar in this sense. So gradient boosting needed the slightly higher learning rate, although very marginally, around 0.1 was a good learning rate for all of these models. We saw that as we got higher in the learning rate, it tended to not that it performed poorly, I guess I would say, but it didn't perform well. I would say it performed worse. Absolutely, you can see that gradient boosting dropped off the highest and the fastest of return of learning. Just was not able to get to a lower level. It wasn't able to slide down the gradient and predict the best model, right? And that's the idea of the boosting, is the next tree is always predicting the errors of the previous tree, and so it can be quite helpful to actually go through this. Okay, so and this would be what you would expect. It's interesting that they all kind of behaved in a similar way. The best scores were around all. The point was, it gives you a lot of confidence that this is going to be a good metric to use if all types of the gradient boosting models, which at the end of the day are using the same types of mathematics, maybe executed slightly different, but this general concept is the same. It's good that we're seeing this. And that would be kind of what I would hope, is that I'm finding similar answers in lots of these. Higher estimators that we found in a couple of these models was kind of interesting to me. You would ideally like to find a lower amount, and something like XGBoost 140. You'd want to use the simplest version of the model that worked the best. And so 490, it just seems a little bit too complicated, but it was the best one, right? And so that could just be this data set that worked the best, and listening to the data, what the data tells me, right? So then we tried the bagging fractions. Is the same thing as subsamples. So the subsample is in the gradient boosting and the XGBoost regressor. It's called bagging fraction here in the LightGBM. Okay, so I'm just doing that, just different model over here, the bagging fraction and subsample, and it didn't make a huge difference. Okay, so especially for the light gradient boosting, you can see the best model performs at about 0.29, 0.39 for gradient boosting, XGBoost 0.239, 0.29, sorry, and it didn't really have an effect. And this is the robustness of the light gradient boosting model. I'm not going to use this parameter in the final model build. It just didn't really make a difference. So I can't really see the point in using this if the default worked just as well. Okay. So now that we've tuned all of these, not super heavy on the scikit-learn and the XGBoost, but we can see here, able to bring up the gradient boosting regressor up to 91.9. Very interesting that the XGBoost, it performs very similar to the XGBoost. I always find XGBoost regressor, aside from in certain, very unique situations, they generally perform very, very similar because they have very simple concepts, similar concepts in the math. We need slightly different models here, but even the learning rate, the subsampler is very similar to each other. The estimators are quite different, but I would wonder if that would really be the case in practice, if we might find something more similar would work well for both of them. Okay. For the LightGBM model, I ended up getting almost a 94. So really the best performing model for today. Worked well. And we can see here that we have the timing is 2 seconds for the gradient boosting regressor, 750 milliseconds, so quite a bit faster for the XGBoost regressor, and it is supposed to be a faster one. We don't know, not always just what the defaults as the defaults are, but as we tune it, I do find that it usually gets to be fast. But here, even faster than that was the LightGBM. So again, 100 milliseconds is maybe not a big deal, but when you're having an application, making these lightning fast decisions could really be the difference in making it user friendly and feeling more intuitive. And so it can often be a good choice, a really good choice for production. Okay. And then just looking at the models, and we can see LGBM, not hugely better, but a little margin better. We were able to squeak out of that model today. And thank you for joining me for the LightGBM model tips video today. I'll see you for the next one. Don't forget to like and subscribe down below.